Hey guys, what's up? Hopefully you started working on this worksheet already. Um, it's really a little bit more involved than the quiz would be. Quiz is going to be more like just working with the notation. You know, we did a lot of that matrix multiplication last time. Really just understanding what the indices do and how to kind of interpret them and things like that. So the worksheet's going to be not quite as involved as, or the worksheet's more involved than the quiz will be, that's for sure. So if you kind of understand what we did from the notes, I would definitely focus on that versus, whatever we did or we're doing today in the worksheet. But the first problem here is pretty easy. And then definitely everything we did in the notes should be familiar. And that's more what the quiz is going to focus on. But this worksheet, let's get started. If we write out a 3x5 matrix of upper indices, we just call it U11, U12, U13, U14, U15, U21, U22, U23, U24, U25, U31, U32, 33, 34, 35. So that's what that matrix would be. It's a 3x5 matrix with upper indices. Both indices are up. Now, part B, both indices are up again. It's a 3x5 matrix, so it's basically going to be the same matrix. U11 up, U12 up, 13 up, 14 up, 15 up. So it's really just the same matrix. And U31 up all the way out to U35 up. So it's just this, it's just saying that the indices, what you call them is not really important. What they represent is what's really important here. So this says D because I skipped a C part, but should really be C. We'll call it D though. So it's a 3x6 matrix, 3 rows, 1, 0, 6 columns. 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. So it'll be a 3x6 matrix of Kronecker delta values. And the Kronecker delta here is because it's only one where I and J are both the same. So, yeah. To calculate the inverse of a matrix, you really just take a matrix like 3, 1, 5, 2, augment it with the identity matrix, and then use row operations to reduce it down to the identity on the left, and then the inverse will end up on the right. So what we could do is we could say like 1/3 times row 1 equals row 1. So it'd be 1, 1/3, 1/3, 0, 5, 2, 0, 1. And then I'm going to replace row 2 by row 2 minus 5, row 1. So 1, 1/3, 1/3, 0. 5 minus 5 will be 0. And then 2 minus 5/3. See, that would be 1/3. So 1/3 goes there. 0 minus 5/3 is negative 5/3. And then 1 minus 0 is 1. And now what I'm going to do is take row 2 and multiply it by 3. So row 2 equals 3 times row 2. So 1, 1/3, 1/3, 0, 0, 1, negative 5, 1. And the last thing is to replace row 1 by row 1 minus 1/3, row 2. And that'll be 1 minus 0, which is 1. 1/3 minus 1/3 is 0. 1/3 plus 5/3 is 6/3, which is 2. And then 0 minus 1/3 is negative 1/3. make sure I'm doing that right. Feels right. Yeah, okay. And then 0, 1, -5, 1. Okay, let's see. Is this the inverse? Unless I made some mistakes somewhere. Help me out. Make sure I didn't make any mistakes. Oh yeah, sure, you could cheat on a 2 by 2. We already know the inverse. It's 1 over the determinant times the adjoint. And the determinant is 6 minus 5, which is 1. So I have it almost right. I messed up the second column. How do I do that? Second column. I'm missing like a multiplication of 3. So anyway, let's see, where did I mess up? Oh, I forgot to multiply this by 3. That's what it was. Right here, this should be a 3. And then when this becomes -1. So yeah, A inverse, or basically the inverse is 2, -1, -5, 3 for the 2 by 2. 3 by 3. Book says something else. Well, I don't know. Let's multiply them out, see what it says. 3, 1, 5, 2 times 2, -1, -5, 3. See that 6 minus 5, which is 1, 3 minus 3, which is 0, 10 minus 10, which is 0, and -5 plus 6, which is 1. Check. So let me double check what you're looking at in the book then. It's 232. Look it up. Two, -1, -5, 3. Yeah, that's what the book says, I think. Oh yeah, sorry. Yeah, my column was wrong. And then the same thing for the 3 by 3. I'm not going to go through it. 3 by 3. Augment it with the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. I mean, you learned to do this in pre-calculus here. So we're not going to spend a whole lot of time doing this. Just to get some more practice. Use the raw operations, reduce it down. Now really where we want to focus is this problem here, because this problem is quite intense. So I'm going to try to take it a little slow, make sure it's going to make sense. But the primes really just denote a different coordinate system. So this is like a different coordinate system. And you could think of this as like Cartesian coordinates. Cartesian, I'm going to call it n-dimensional Cartesian coordinates, or something like that. So primes are just a different coordinate system. Unprimes are the original coordinate system, like the Cartesian coordinate system. Part A says, show that for independent functions xi prime, that this relationship right here is true. Okay, let me zoom out a little bit. Part A, partial xi prime, partial xj prime is equal to delta I prime j prime, since xi prime and xj prime are independent variables. So that's how we get the delta I prime j prime on the right. Now, how do we get the thing on the left? Well, that's just the multivariable chain rule. So also, by the multivariable chain rule, partial xi prime partial xj prime will be equal to partial xi prime partial xr partial xr partial xj prime. And of course there's a summation happening there, so I'm skipping writing the summation symbol because I'm invoking the Einstein summation. But that's the that's the multivariable chain rule in a nutshell. So then these two have to be equal. So partial xi prime partial xr partial xr partial xj prime be equal to delta I prime j prime. So extremely useful. It's like a way to reduce things down to deltas, and we're going to have a bunch of these in chapter 3, 4, 5, and 6. And whenever we see something like this, we'll just change it into a delta. So we like these things to be deltas. So we basically like to undo the multivariable chain rule and reduce it down to a delta. Now, part B says, take the partial derivative of the previous relationship to show the following. Oh man. Well, okay. Take the partial derivative of the previous relationship with respect to k, we'll call it. So, part B, partial xk of partial xi prime partial xr partial xr partial xj prime equals partial xk of delta I prime j prime. Well, on the left it's a product rule. Product rule on the left equals 0, because on the right you're just taking derivative of a constant. Delta I prime j prime equals 1 or 0. So either way, its derivative is going to be 0. No matter which variable xk you differentiate with respect to, the derivative is going to be 0. So now all that's left to do is take the product rule on the left. So x prime or xi prime of xr is a function of x and r. So this would be partial squared xi prime partial xk partial xr times partial xr partial xj prime plus partial xk of partial xr partial xj prime times partial xi prime partial xr. So I'm doing the product rule, and now this function is a function of the primes. So this is a function of x prime coordinates. So use chain rule. To differentiate this with respect to xk. So this is going to be, well, it's already equal to 0. And now this one is just partial squared xi prime, partial xk, partial xr, partial xr, partial xj prime, plus, well, first I'd have to differentiate with respect to prime coordinates. I'm going to do partial squared xr, partial xs prime, partial xj prime, and then differentiate partial xs prime with respect to xk. And then multiply that just by partial I prime, partial xr equals 0. And then move that thing to the right, and we get the relationship that we wanted. It's partial squared xi prime, partial xk, partial xr, partial xr, partial xj prime equals negative partial squared xr, partial xs prime, partial x j prime, partial x s prime, partial x k, partial x I prime, partial x r. And that is the relationship we wanted to verify. Yes. So note right here, I'm differentiating xr with respect to xk. Well, to do that, I have to go through the prime coordinates, which is why we introduced this s prime here and here. So use a chain rule to do that derivative. And then part C, it says verify the relationship in A is true for switching from Cartesian to polar coordinates. So x1, x2 is Cartesian, and then r and theta is x1 prime, x2 prime. So the relationship is basically going to be that partial r, partial x, partial x, partial, well, let's say r plus partial r, partial y, partial y, partial r equals 1. So show. Also show partial r, partial x, partial theta plus partial r, partial y, partial theta equals 0. Partial theta, partial x, partial theta plus partial theta, partial y, partial theta equals 1. And then partial theta, partial x, partial r plus partial theta, partial y, partial r equals 0. So we need to show that these four work out explicitly, even though we've shown it generally. We just want to show, for example, that it does work for Cartesian to polar. So to do this, we need to write out the equations for Cartesian to polar. So that's x equals r cosine theta, y equals r sine theta, r equals square root of x squared plus y squared, and theta equals arctan y over x. Possibly plus pi, but that's going to go away if we differentiate anyway, so I'm just going to leave it as arctan y over x. So let's calculate a couple of things here. Partial r, partial x equals, let's see, it's just x over square root of x squared plus y squared, which would be r cosine theta over r, which would be cosine theta. Partial x, partial r is this cosine theta. Partial r, partial y is y over square root of x squared plus y squared, which would be r sine theta over r, which is sine theta. And then lastly, partial y, partial r would be sine theta. So the first one, so number one is cosine squared theta plus sine squared theta on the left equals 1. Check. So the relationship holds for at least the first one, basically taking partial r, but expanding it out with a chain rule in between. Oh, sine squared theta. All right, so that's the first one there, partial r. What else do we need? We might need like partial x, partial theta. Partial x, partial theta would be negative r sine theta. And partial y, partial theta would be r cosine theta. So now number two would be cosine theta times negative r sine theta plus sine theta times r cosine theta, which is 0. Check. Number 3, partial theta, partial x. Let's see, we haven't done that. So partial theta, partial x. Oh, that's nasty. Arctan is 1 over 1 plus y over x squared. Derivative with respect to x, though, is going to be times negative y over x squared, which is negative y over x squared plus y squared, which will be negative and then r sine theta over r squared, which is sine theta over r, negative sine theta over r. And then similarly, partial theta, partial y will be 1 over 1 plus y over x squared times derivative with respect to y of y over x is just 1 over x. So that's going to be x over x squared plus y squared, which is r cosine theta over r squared, which is cosine theta over r. So number 3 is, let's see, partial theta, partial x, which is negative sine theta over r times partial x, partial theta. X of theta was negative r sine theta plus partial theta, partial y, which is cosine theta over r times partial x, partial y, partial theta, which is r cosine theta, which is sine squared theta plus cosine squared theta, which is 1. Check. And then the last one, partial theta, partial x, is negative sine theta over r times, let's see, partial x, partial r is cosine theta plus cosine theta over r times partial y, partial r is sine theta, which is 0. Check. So that verifies that the relationship we derived in part A is true for cool. So that's pretty much it for the worksheet. Like I said, the worksheet is going to be this problem is definitely more involved than the worksheet. The worksheet is going to be just straightforward. It's going to be like 3 questions, mostly focusing on like using indices for like matrix multiplication and doing stuff for like just writing out matrices and stuff like that. So not a big deal. Definitely not like this last problem. So cool. Yeah. Anyway, hit me up on the Discord. I'll catch you guys next time. If there are any questions, yeah, let's just hang out. But I'll see you guys later.